Everyone, welcome to session 7 of EMSOFT 2022, and this session is about verification and machine learning. We have 4 talks in this session, and the first talk will be given by Samvid Mistry from GitHub. Okay. Hi Samvid, so you can please go ahead and start with your presentation.
Thank you. Is everybody seeing my screen?
Yes.
Okay, thank you. So, hello everyone. I'm going to present an MILP encoding for efficient verification of quantized DNNs. I am Samvid, and this work was carried out along with my supervisors, Professor Indranil Saha and Professor Swarnendu Biswas. So it has been shown that quantized neural networks introduce little degradation to the network's accuracy while still giving us significant benefits in terms of memory and latency. So these are some stats about that. And but it has been also shown that they are not immune to adversarial attacks. I have shown a couple of adversarial attacks here. You can see that we have an image of panda, which when infused with a little bit of imperceptible noise, makes a neural network classified as given with very high confidence. So looking at the process between conversion of floating point numbers to fixed point numbers and vice versa, we have this network, and for denoting the fixed point numbers, we are going to use a notation called Q point. So Q point is simply Q followed by the number of integer bits followed by dot followed by the number of fractional bits. As an example, a Q4.4 number would be a fixed point number with 4 integer and 4 fractional bits. Now we are going to assume that all the numbers in this presentation are going to be of type Q4.4 for the sake of simplicity. So now when you multiply two fixed point numbers, let's say Qa.b and Qb.q, then in the worst case, the result can be as large as Qa plus b dot b plus q. Now you cannot use this resulting number in further computations because all types are Q4.4. So if we say, for example, multiply Q4.4 number with another 4.4 number, we're going to get a Q8.8 number, which we have to condense down back to Q4.4. So to get the fractional part in control, we are going to shift it right by 4 bits, and that will give you a Q8.4 number. Now you take the largest and the smallest number representable by Q4.4 number and saturate the Q8.4 number between these two bounds to get a Q4.4 number. So that is how we are going to get the bit width in control. Now let's see how to convert floating point and fixed point numbers in between. So to convert a floating point number to fixed point number, we're just going to multiply by 2 to the number of fractional bits, and then we're going to get rid of the whatever fractional part is left. Now the function int that I've shown here is actually a function which can round the number down towards negative infinity. As I mentioned, all nodes will have type Q4.4. Now if we assume that x1 has the value 2.09375, when we convert it to the Q4.4 type, we're going to get the number 33. Same goes for x2, we'll get a number 16. Now if we plug 33 and 16 as the input values on the above network, the resulting value of y1 is going to be 33 again. Now we need to convert this y1 value, the value of 33, back to 45. So for that we are going to just divide the fixed point number by 2 to the number of fractional bits. In this case, 33 divided by 2 to the 4 is going to be 2.0625. Now this is the standard procedure, and the difficulty while encoding this procedure into a mixed integer linear program is that there is no primitive to round the numbers. So it is not possible to directly implement the int function that we have shown here. To implement rounding, we are going to present a set of novel equations which can soundly encode this rounding operation in a mixed integer linear program. I'm going to show it by an example. So let's say we have beta bar equals 55 and we want to shift it right by 2 bits. So f is equal to 2. So when we multiply eta bar by 2 to the negative 2, we get 13.75. Now we want to round this number down and assign to zeta bar. So as we can see, the value of zeta bar is going to be 13. Now before I show the equations, there's a value that we have to choose called offset. Now offset must be chosen such that it is greater than or equal to 1 minus 2 to the negative number of fractional bits, and the upper bound is 1. In this case, if we plug the values, we get 0.75 must be less than equal to offset, must be less than 1. Let's choose 0.75 as offset. And these are the two equations that are used to soundly encode the rounding operation in a mixed linear program. Now, if you substitute the values, you'll see that we'll get 13 must be less than or equal to zeta bar, and zeta bar must be less than or equal to 30.75. Now, since zeta bar is an integer variable, the only value that satisfies both the equations is 13, and 13 is going to be assigned to zeta bar by the MILP solver. Now, this is the procedure at a high level which will follow to encode a quantized neural network into a mixed linear program. I'm going to show the stages for an example. Let's again take this neural network. I'm going to expand the intermediate layer to show the intermediate variables. So this is the whole procedure. When we look at the input values, you would already know the bounds for the input, the highest and lowest value you can get. So you can directly convert the floating point values to fixed point and then constrain the inputs by those values. In this case, the bounds for A11 would be 33 and 48. The bounds for A12 is 8 and 16. Now, if your inputs have different types, then this is the point where you would try to align all those radical points. In this case, all types are same, all types are Q4.4. So we're just directly going to copy the values over to X. Now we're going to multiply the weights and then add biases. All the values are again converted to Q4.4. So this is a multiplication of Q4.4 number with another Q4.4 number. And as I mentioned, the result can be as large as Q8.8. So we're going to shift it by right and round it down to get a Q8.4 number. And this is where the equations that I showed you in the previous slide are going to be used to round the number down. So as you can see, I have used the two equations shown in the previous slide along with multiplication with 2 to the negative 4, which will shift the number to the right by 4 and then round it down. Next up, we are just going to saturate the number between the bounds for a Q4.4 value. And finally, we are going to apply the activation function. In this case, it is prelude. Now, quickly looking at the experimental setup, our solution is implemented in Python using Gurobi as the backend MILP solver. It is going to be referred to as MILP from now on. We compare with another implementation which uses PySMT with Collector as the SMT solver in the backend, referred to as BBSMT. And then another implementation which improves on BBSMT, referred to as BB2SMT. The benchmarks we are going to use are MNIST, collision avoidance, Mistry, and AKSXU, which are all standard benchmarks in the neural network literature. And these are the references for the implementations. For MNIST, we have 4 networks that we tested with and total 315 instances. For single-threaded MILP, we passed 290 instances out of 315 within time limit. And for multi-threaded MILP, we passed all the instances within time limit. Now, in comparison, the BBSMT timed out on all the instances in case of MNIST. Looking at other benchmarks, in collision avoidance, we saw 10 times improvement on BBSMT with a single thread, and with multiple threads, we saw 15 times improvement. For twin stream, on average, we saw 2.26 times improvement with single thread and 2.5 times in multi-threaded. And finally, for AKS, we saw 2.5 times improvement with a single thread and 13 times improvement with multiple threads. The caveat for AKSXU is that BBSMT encountered only 5 timeouts, while single-threaded MILP encountered 40 and multi-threaded MILP encountered 20 timeouts. Looking at BB2SMT, for MNIST-C, we performed 15 times faster on average, and for Passion-C, we performed 8.5 times faster. And you can see that the gap between mean and median is very less, which means that the MILP solver is performing very fast consistently and not just on some instances. To conclude, we saw an order of magnitude improvement in multiple standard benchmarks, and this makes it possible to verify larger networks in practice than previously possible. However, the performance can be less than satisfactory in some instances, and the code and data that is used for all these experiments is available at the following link. Thank you.
Thanks, Samvid. We have time for questions. So any question from the audience? Okay, so Clarisse, please go ahead. Yeah.
Yes, hello. Thank you for the presentation. Could you explain on me what kind of property you can check? Can you check, for instance, the distance between a float point encoding compared to a fixed point encoding?
You'd have to define the, like, what do you mean by distance?
Compare the output of a neural network, how far it is, and let's say after I have the argmin or argmax, whatever, can I compare if it's a classification, whether it's the same classification? Can you check this kind of property with your encoding?
Yeah. So as far as I understand, you mean that you want to find out the difference between the output of a floating point network versus what the fixed point network would give.
Exactly.
Right?
Exactly.
Yeah.
I want to compare the quantized version of the non-quantized.
Yeah. Okay. Got it. So what you can do is, I mean, it is not directly explained in the paper, but what you can do is you can have a separate encoding for the floating point network, and then have a separate encoding for the fixed point network, and then you can add a constraint which can maximize the difference between the floating point and the fixed point network. Now, since it's a mixed integer linear programming solvers, which are already designed to optimize the equations, it is it should be possible to get the output of that optimization.
Okay. Thanks.
Thanks, Clary. Other questions? Okay, if not, let's thank the speaker. And we can move.
Thank you very much.
Talk. Okay, so the next speaker is Banghu from National University of Defense Technology. Banghu, please share your screen.
Hello, everyone. Can you hear me?
Yes, yes.
Okay.
So please.
Hello, everyone. I am Banghu Yin. I will introduce our work about efficient complete verification of neural networks for layerized splitting and refinement. Firstly, I will introduce our motivation. A neural network computes input-output relationship, which can be recorded as a function f. And the verification problem is to check that if the input belongs to some set of x, then the output will belong to some set of y. Here is a motivating example. This network has two inputs, two hidden layers, and one output. The verification problem is to check if x and y are taking values from 0 to 1. The output S3 is never larger than 0. For a neural network verification problem, if a verifier returns true and the property is actually true, then the verifier is sound. On the contrary, we say the verifier is complete. A recent survey classified neural networks verification methods by considering a verifier is complete or not, and found that complete methods are hard to scale. There are many two types of complete methods. The first type is SMT or MILP server-based verification, such as Planet realplex, which greatly depends on the server's efficiency. The second type is the BNB-based verification, such as Resolver Marlboro. Our target is achieving more efficient and complete verification fitting into BNB framework. Our framework firstly takes a single pass abstract analysis. If the property is proved, then return. Otherwise, we do splitting and refinement, which make more neuers become deterministic. For each sub-verification problem, we repeat above procedure until all sub-problems are verified to be true or counterexamples are found. We firstly introduce the single-pass abstract analysis, short for SPAA. For each neuer S of abstract representment is as following. SB represents the load before performing ReLU on S, and SF represents that after ReLU. The activation state of S is denoted as AS, and we record the states of SB and SF with symbolic bounds SBS and value bound VBS. SBS are linear expressions over input variables. VBS are computed on SBS and input value range. AS is determined by VBS. In SPAA, we introduce a new linear reduction on ReLU. It is easy to compute SF if the activation state of S is deterministic. If S is undeterministic, we propose the following linear reduction strategy, which has achieved the smallest error of precision loss. For our motivating example, for neuer S1, we firstly compute its symbolic and value bounds like this, then compute its activation state, which is unknown, since the value range includes 0. Finally, we can compute its symbolic bound after performing linear reduction. Similarly, we can compute the states of S2 and S3. The second technique is splitting by FUL strategy. The splitting strategy includes 2 steps. The first one is to choose undeterministic neuer T in FUL as splitting neuer. FUL is the first layer with undeterministic neuers. The second step is splitting on omega based on T and the update S, where omega is a set of linear constraints on input variables. The results are as following. Note that after splitting by FUL strategy, the splitting neuer must be deterministic in both sub-VPS, and this property makes over approach be complete. In our motivating example, since the activation state of S1 is unknown, thus layer 1 is FUL. Then we choose S1 as splitting node. Its symbolic bound is 3x minus 2y. Before splitting, suppose omega is like this. Activation state of S1 is unknown. After splitting on S1, in sub VP1, omega is like this, and S1 is becoming active. In sub VP2, omega 2 is like this, and S1 becomes inactive. The third technique is about input refinement. For each sub VP, input range can be refined based on omega by solving linear program problems. In our motivating example, in sub VPS, we can get the following refined input ranges. After refining X, more neuers become deterministic during next SPAA. The speculative strategy is to refine the input range every m times of splitting. Then we can achieve balance between precision and efficiency by configuring M. For our motivating example, after the first SPAA, the property is unknown. Then we do FUL splitting and import refinement and get two sub-VPS. For sub-VP1, the property can be verified by another SPAA. And for sub-VP2, property is verified directly since input range is empty. Now I will introduce our experiment. We have implemented a dual layers using OpenBlast LP server and multi-threading technique. The data sets mainly include Aiguo and MILP. Our experiment has two parts. The first one is comparing with other complete verifiers. The second part is to evaluate the contribution of each technique. We first conduct comparison on verifying safety property on Aiguo. The result is as following. The red line is the result of Layerwised, which shows that Layerwised has verified more properties with less time. The table gives detailed speedups of Layerwised over these verifiers. Experimental results show that the approach is efficient. Then we conduct comparison by robustness property on MILP. From the results, we can find that when robustness radius epsilon is small, 3 tools can verify most of these properties. But as epsilon getting larger, the underlying model tends to become unsafe. More and more contact examples can be found by Layerwised. This result indicates that Layerwised can generate contact examples more efficiently than other truth verifiers. During ablation study, we found that the average speedups is around 1.2 times when comparing over linear reduction with linear reductions proposed in deploy and verify. For splitting strategy, we also found that first, the non-FUL strategy may be incomplete. Second, the FUL strategy is much faster than the non-FUL ones. For import refinement technique, and we found that first, it helps to improve Layerwised efficiency greatly. Second, Layerwised can be more efficient with a suitable speculative number M. For more, for the ablation study, please read our paper for more details. Now we conclude our paper. This work is about verification of neural networks. We have introduced our verification framework. It includes 3 new proposed techniques which make our approach complete and efficient. We implemented a dual layers. We conducted experiments on both verifying safety property on Aiguo and the robustness property on MILP. The result is promising when compared with some state-of-the-art verifiers. Okay, thank you.
Yeah, thanks, Banghu, for your nice talk. It's time for questions. Any questions from the audience? Okay, so apparently there is no questions from the audience. Let me ask you a question. So in terms of scalability, so how do you think your method will scale up when you increase the number of layers in the neural network?
You mean the scalability of my approach?
Yeah, because so if I understood correctly, you are splitting in between, right? And
Yes.
so if you increase the number of layers, right?
Yes.
So don't you think the number of possibilities that will kind of explode with the number of layers? Or I mean, did you study how, you know, like your verification scale up with, you know, so when you okay, so that size of the network that you have considered for your exam experiments, so what is the maximum size of neural network that you have dealt with?
Yes, actually, the scalability for our data set, we use the millist, the number of new years is about 1,000 yes, and the scalability is hard. Since we have trying to achieve the complete verification, so the scalability is hard. Is a big problem for our verification. You know, since we have to verify the property definitely. We must return true or give a counter example. So this approach is comparing with other verification methods with abstraction, and the our approach is not so scalable, I think. Yeah.
Okay. Okay. Thanks.
Okay. Thank you.
Any questions from the audience? Okay, so if not, let's thank Banghu once again.
Thank you.
And for this nice talk. And then I think we can move to the next talk. Yeah, the next talk is on Tardis, coverage guided embedded operating system fuzzing. And this talk will be given by Yuheng Shen from Tsinghua University. So,
hi, can you hear me?
Yuheng, yes, I can hear you, but I cannot see your screen.
Okay, wait a second.
Yeah, I can see you also now.
Okay. Okay, so hello everyone, it's Yuheng from Tsinghua University. It's my pleasure to introduce you with Tardis, the coverage guided fuzz testing on embedded operating systems. So first, what is an embedded operating systems? An embedded operating systems is an operating system that is specially designed to run specialized tasks under the embedded environment. They are widely used in many mission critical situations, such as the aerospace industrials and autonomous vehicles. However, there are huge differences compared to embedded operating systems and general purpose operating systems. So first, the architecture for them can be considerably less, and the memory space can be less. Also, they reduce many unneeded features and interfaces to improve the predictability of its runtime behavior. Third, the embedded operating system often designed to integrate this code with userland code into an application as a single executable image. So the fuzz testing, also known as fuzzing, is the vulnerability detection techniques. There are many famous kernel fuzzers like syscallers and healers. The coverage guided kernel fuzzers uses kcoff to instrument the target kernel. Then feed the kernel runs on a virtualized environment like the QMU with system call sequence. So if the fuzzer identifies any new system call sequence that triggers the new code coverage, the fuzzer will save it for further mutations. So there are huge challenges importing the general purpose operating system fuzzing to the embedded operating system fuzzing. So first, the embedded operating system targets a wide variety of architecture, which prevent the fuzzers from leveraging many hardware features to assist the fuzzing relevant operations. And second, they often do not provide a unified interface to interact with the userland code. And third, the coverage collection and the coverage analysis mechanism should be highly efficient, thus reduce the impact on the fuzzing throughput. Therefore, we propose the Tardis. The Tardis uses the embedded operating system source code as the input, and it will compile it into the instrument image. And then we will boot this instrument image through the Cumul emulators. And during its first startup, we will dynamically initialize the coverage collection mechanisms. And then the fuzz engines will collect some random corpse from a database and send this test cases to the instrument, the image. And the coverage collection mechanisms will then collect the runtime coverage and store them into the host to VM coverage buffers. And at the host side, the coverage analysis mechanisms will then read these coverage information from this coverage buffer and convert it to a compact bitmap. And then we will analyze it to find if there are new paths we have triggered. And then we will save this corp, and we'll save these test cases in corps for further generations and mutations. So first, we propose this dynamically initialization mechanisms. We will initialize the coverage by utilizing PC-Triscott init functions to assign ID to each basic block. The existing mechanisms for the coverage collection initialization cannot invoke during the kernel booting phase due to the diverse runtime mode and inadequate compilation support. So to properly initialize these functions, we pinpoint the address of these functions during the compiling times. Then we implement a direct cost to it during the OS startup through the function pointers. And then for the OS agnostic coverage collection mechanisms, we insert the PC-Triscott functions at every basic block to collect the edge coverage. However, the existing coverage collection tools like Kickoff, utilizing many sophisticated services from the target operating systems, like the MapMap operations and fopen operations, which are not always supported on the embedded operating systems. So Tardis collect the coverage by utilizing the ID assigned to each basic block. Using the XOR simple operations, the previously converted basic block and the current basic block, the Tardis can have a unique ID for each edge. And then we will statistic this hit counts for every edge as the overall coverage information. So we then propose the host to VM coverage buffers. The Tardis expose certain data files within Cumul, like the coverage buffers, and we do it by modifying the Cumul and using the shell memory mechanisms. In this way, Tardis can access the coverage buffer at the host and read this coverage information in a target ignorant ways. And then for the efficient analysis in the host, we analyze this coverage utilizing a compact bitmap, using a classification field to convert the edge coverage into a binary form. Then we can compare the local coverage with the global coverage through simple binary operations. So we implement Tardis in Rust, and now it supports MuleCos, FreeRTOS, Zephyr, and anti-threat fuzzings. On the host side, we manage the whole fuzzing process and the test case generations. The guest segment deal with the system called deserialization and test cases execution. The instrumentation is implemented based on the C-long compilers. So for evaluation, we first propose 3 research questions. First, is Tardis able to uncover new vulnerabilities in different operating systems? And second, is the coverage guided mechanism really effective in terms of achieving a higher code coverage? And third, what is the overhead as the instrument brings to the Tardis? And first, for the bug detection capabilities, Tardis found a total number of 17 previously unknown bugs within the 4 embedded operating systems, among which many has been confirmed and repaired by the maintainers. And for the coverage comparisons, we designed the Tardis miners, which in turn is the Tardis without the coverage guidance functions. And on average, Tardis gains about 15% of the coverage improvements. But however, we only provide a description for some core modules with limited test cases. So this could lead to the fuzzing campaign easily to reach the saturation stage. So for the overhead evaluations, the memory of overhead for all 4 embedded operating systems about 27% on average, and the instrumentation leads to an average execution overhead about 13%. And that'll be all. Thanks.
Yeah. Thanks, Yuheng, for your nice talk.
Yes.
We have plenty of time for questions. Yeah, Pascal, you have a question, please go ahead with your question.
Hi, thank you for the talk and for the question opportunity. Okay, so I just want to know two questions. The first is the source code of Tardis, is it open?
No.
And then secondly,
sorry, Tardis is now still under the development phase, so it's won't open source for now.
okay. Then secondly, I just want to know, so when you are fuzzing, let's say a software like FerrAutos, and you're trying to fuzz the kernel of FerrAutos, for example, the kernel does not really expose, let's say command line interface or something you can interact with. So how do you send your fuzz data to FerrAutos kernel?
Sorry, I'm not quite catch up with you. So do you mean that how do we send the test input into the kernel or something else?
Yeah.
So basically, we include the kernel's header files, and which they provide us with many the system call sequence. So we just call this system call sequence to trigger the kernel code, and that's how we test it. So basically we test the kernel through the system call, and we call this system calls through the function pointer.
Okay, so it's more like you just you include the header files to your fuzzing harness, and then
yes.
Okay, but then when you do that, so while fuzzing, let's say FerrAutos, does the FerrAutos scheduler need to be running for the fuzzing to be effective?
Sorry, I'm not quite catch up with you.
Okay, I mean, when fuzzing the FerrAutos, does the FerrAutos scheduler, does it need to be running for the fuzzing to be effective?
Yes, we have to run in the kernel, actually runs the kernel that the test can be started.
Okay, thank you.
Yes, you're welcome.
Yeah, thanks
For your
questions. So I have one question. So when you say coverage, right, how exactly do you define coverage? So do you have one specific coverage criteria, or do you have many different coverage criteria based on which you perform your testing?
Yes, we need to have few these things to do the fuzzing.
Okay, so when you say coverage, what does that exactly mean? What do you cover? Is it, you mentioned edge coverage?
Yes, we use this coverage to guide the further fuzzing. So, for example, if a test cases or if a system call sequence that triggers a new code coverage, so it gives us a higher chance of testing the unknown kernel code. And in this way, we can boost the fuzzing efficiency and let us to test more deeper into the kernel code.
Right, but when I say coverage, say for example, a coverage of a program or software, I can think of say statement coverage or say branch coverage or even path coverage, right? So do you have any such concrete criteria? So what exactly do you cover when you say that okay, it's a coverage?
The branch coverage,
Okay, so it's a branch coverage. Okay.
Yes.
Okay, but do you think that you could also extend it to other coverage criteria?
Yes, I think that so we implement these coverage collections based on the CLAN. So it provides us with something just besides the branch coverage. We can do it in the line coverage. So we can statistical what lines do we hit, and we can statistical what edge do we cover, and we can statistical what functions do we cover. We can collect this coverage collections is customized.
Okay. And okay, I think that's good. Okay, any other questions? Okay, so apparently there is no other question. Then thank you again. Your nice talk and for answering. Okay, so there is one question. So I think Clary has a question. Clary, please go ahead with the question. We have time. Oh, Clary is actually uploaded.
Just
Okay, no,
clapping.
yeah, okay, sorry, I missed it. Okay, then I think yeah, thanks. We can move to the next talk.
So, okay, thanks.
So the fourth talk, it's on formal verification of resource synchronization protocol implementation, a case study in RTEMS. And the talk will be given by Zunze Shi from TU Dortmund. Yes. Yeah, Zunze, I can see your screen.
Yes.
I can hear you. Yes.
Yeah, okay. So can you hear me?
Yes, everything is
okay. Great. So hello everyone. My name is Jingjie Shan from TU Dortmund. Today I'm going to share our work formal verification of resource synchronization protocol implementations, case study in Atoms. This work is collaborated by TU Dortmund and University of Twente and supported by DFG project SFB 876 and ERC project PROPER-RT. So in concurrent real-time systems, mutually exclusively access to shared resources like shared memory, external devices, and shared data prevent data corruptions and risk conditions. The execution of shared resources are usually called critical sessions. Binary semaphores or mutex locks are applied to protect the mutually exclusive executions of critical sessions. In the example, we can see, although the Tau2 has a higher priority, once Tau1 starts the execution of its critical session, Tau2 cannot access it anymore. So in the past decades, a lot of resource synchronization protocols have been developed and analyzed. For example, priority ceiling protocol for uniprocessor and distributed PCP, multiprocessor PCP, and MRSP for multiprocessor real-time systems. Such a protocol can be formally described as a set of rules that are composed of abstracted system models under certain assumptions at the operating system level. So, however, these abstractions and assumptions may not always hold while realizing a protocol. For example, some operating systems may not allow multiple tasks with the same priority, whereas the inherited ceiling priority, like in ICPP, has to be compensated by setting ceiling priorities differently and excluding these priorities from regular priorities that have been assigned to other tasks. Any necessary adaptations due to the constraint imposed by the operating system in practice may lead to a mismatch to the original specifications, resulting in unexpected consequences. So, several previous works mainly focus on formal verification of the real-time operating systems, for example, SEL4 and CTKOS. In this work, we focus on the formal verification of synchronization protocols implemented in real-time operating systems by assuming the underlying functionalities are correct. We propose to contract the obligations of involved primitives and operations and apply the deductive verification on the corresponding implementation of a protocol in a targeted OS. We present a framework for formally verifying the properties of the synchronization protocol implementations in a given OS. We provide 2 case studies to verify ICPP and MRSP implemented in the official atoms. In consequence, we discover long state mismatches and provide possible remedies for both protocols. So the formal description of a protocol are based on abstracting from operating systems or hardware-specific details. To specify a certain property of a program, a Hora triple of a form, precondition, program, post condition is formulated, where the post condition post holds if the program is executed with fulfilled precondition pre. If a post condition is supposed to hold in any possible case, the precondition is just true. To check such a property against a problem, its weakest precondition WP that is required to satisfy the post condition is derived. If the defined precondition pre implies the derived WP, the property is proven to hold for the analyzed program. We provide an example. Consider a function absolute division x and y that divides the absolute value of x by y. So since the division by 0 is illegal, so the function will return -1, the desired behavior, the property can be formulated as follows, where the res is the value returned by the absolute division. The weakest precondition is y is not equals to 0. So the plugin WP, the weakest precondition of framework C, provides static analysis and the deductive verification of source code. So in this work, only the implementation of protocols is verified. The proposed framework is applied to verify the correctness of the implementation for all the specified properties from a given protocol, like function contracts. More precisely, the proposed framework assumes that an implemented resource synchronization protocol is based on a correct underlying operating system. The workflow of our framework can be described as follows. First, we identify the subset of the targeted operating system source code that represents the protocol implementation. Secondly, we identify the resource synchronization protocol's properties and the rules, like the request and the releases of resources. Thirdly, we design the specifications consisting of horror triples for the behavior of all utilized operating primitives and the protocol implementation based on the formal specification of the protocol. And last, we verify the specification of the implementation against its source code with deductive program verification added by appropriate software. So we first verify the immediate ceiling priority protocol on atoms. When attempting to verify the called set owner function, the verification fails to prove the ceiling check and parts of the successful acquisition. In ICPP, a resource ceiling is set as the highest base priority of all requesting tasks. A task should not have higher priority than the ceiling of the requested resource. When a task tries to lock a resource, the requested resource's ceiling is checked against the task's current dynamic priority. The deadlock can happen if nested resource access in descending order of priorities. Consider two tasks, Tau1 and Tau2. When Tau2 has higher priority and the two resources, R1 used by both tasks and R2 used only by Tau1. R1 has a higher priority ceiling and R2 has a lower priority ceiling. If Tau1 acquires R1, it inherits its priority ceiling and executes with a promoted dynamic high priority. If it requests the second resource R2, its dynamic priority is higher than R2 ceiling's priority, which leads to a denial of the resource access by implemented ceiling check. The consequence of this is a deadlock. So Tau1 holds R1, but cannot successfully lock the semaphore R2 due to the implemented ceiling check, whilst Tau2 cannot enter the critical session guarded by R1. An acquisition in the opposite order would be accepted. So to correct the mismatch, an adaptation to the priority ceiling check is proposed. Instead of checking the potential already increased dynamic priority, it utilized the thread base priority for the comparison to the newly requested resources priority ceiling. After applying the correction, all stated properties are successfully verified. We also verify the official implementation of MRSP in atoms. So the official implementation of the size operation of MRSP in atoms does not allow an arbitrary sequence of resource requests if they are not properly nested. We have to additionally introduce an assumption. So a thread acquiring nested resources always requests them in a non-descending order of priority ceiling. together with derived function contracts. So after applying the remedy of ICPP and the introduced assumption, all the implemented functions are successfully verified. So in this work, we present a pragmatic framework to verify the existing protocol implementations in real-time operating systems. We propose to specify the intended behavior of the implementation in the form of function contracts. The deductive verification is applied to verify whether each implemented components match its formally described properties under the assumption that underlying primitives are implemented correctly. We propose a verification framework to enable modular formal verification of functional components. The analysis target is defined and isolated from its dependencies. So the workflow of the proposed framework is conceptually independent to the platform. So the case study of ICPP and MRSP implemented in Atoms shows the applicability of the proposed verification framework to an actual real-time operating system. Moreover, the discovery of the mismatch in the Atoms implementations shows its functionality. After proposed correction, the implementation of ICPP and MRSP under one additional assumption can be successfully verified. So thank you.
Yeah, thanks, Ranjay. Very nice talk. So we have plenty of time for questions. Any question from the audience? Okay. So yeah, I have a few questions.
Yes, please.
So you have used this deductive verification technique in your work, right?
Yes.
So for protocol verification, another widely used technique is model checking. Right?
Yes.
And then so maybe I don't know if you look at like real-time properties or like non-real-time properties. Depending on that, that there are model checkers that one could also use to verify, like the kind of properties you are verifying. So how do you compare your deductive verification technique with model checking techniques in terms of, say, like the manual effort that might need to be invested?
Okay, so in our deductive verification, so since we already got the source codes like the official implemented in Atoms, so we can straightforwardly to verify the implementation and to check whether the implementation matches the formal description of the protocol. But for the model-based checking, we have to build the model, and so it will introduce, relatively, so we will suffer from the relatively high risk that we introduce new errors during the verification. Yeah. Okay, so you are saying that you have the implementation, so it is easier to use that code itself. And if I want to do model checking, then I have to first create a model, and in that process might introduce errors, right? So yes. Okay, very nice. And is there any question? Let me check. Otherwise, let me ask my second question. So you mentioned that you have verified the subset of implementation, right? And then if you go back to your slide 4, and then you are talking about modular formal verification, right? Hold on. Which one? This one?
Yeah, this subset of protocol implementation, and then you are performing modular verification, right? So when I have a protocol, I might have high-level specification that I want the protocol to satisfy, right, during its execution. Now, if I want to look at, say a subset of this protocol implementation, maybe I have to think about some property that holds for the subset, right? So maybe I have to also think about adapting my property to the specific subset that I am looking into, right, for verification. So this is one thing. And second thing is that for modular verification also, so this identifying precondition and postcondition, was it easy from the implementation? did you get to identify the precondition and postcondition easily from the implementation, or how did you do that? So that's what.
Yeah, so the first step of our verification framework is to we have to isolate the protocol implementation from the real-time operating system source code, right? So that we also assume that the low-level functions like the threads, the queues, the mutex, the context switch, we assume these low-level functions are correct, and we only look for the implementation of the protocol itself. So that's why we said it's the subset of protocol implementation. And for the precondition and the post-condition, so they are generated from the formal description of the protocol. So I mean the thread, the theory of the protocol, not the implementation of protocol. So we try to find the mismatch between the formal description of the protocol and the implementation on real-time operating systems. So it's like we try to abstract the description of try to abstract the formal description of the protocol and to check the matchness between the description and the implementation. So yeah, and also you said that, yeah. Also, you said the user behavior. The user behavior is like so we have to distinguish between the correctness of the implementation and the correctly utilization of the protocol. So they are different, right? So although we implemented it correctly, but the users can also use it wrongly, and they can set something wrong. But the only thing that the only thing that we can do is to make sure our implementation is correct, and also we need to do some documentation to guide the users to use it correctly. So I think, yeah.
So do you think that you identify the ways of wrongly using the protocol by the user, and this kind of technique helps you in documenting such?
So we only try to make sure that our protocols, so these protocols are implemented, match the formal description, so match the formal design or the original design of the protocol. But how the users utilize this protocol, or how they implement their own task set or their own application is not our focus, right? So yeah.
But generally, you know, like the users will be treated as environment, and you will have some assumptions on their behavior, right?
Yes,
so,
yes. But then they have to, I mean, yeah, I think the documentation is also one of the big issue of this real-time operating system, since the users may not that familiar with the behavior of the operating system, so they have to follow the guidance or follow the API to do that. Then we need a very detailed description or some barrier function, like to check if their functions or their the priority ceilings are set correctly, right? So in Artemis, the priority ceiling is normally given by users, but if the user sets the ceiling wrongly, then the protocol, I mean, cannot perform correctly, right? So I mean, we can provide some checking, but I think that is not the main focus of this work.
Yeah. Okay, thanks for your presentation and also answering my questions.
Yeah,
I think so. Thanks, Zunzi. Then I think we are at the end of this session. So there is a poster session, I think, after the next session. And I think that poster session is also in the hybrid mode. So please, like attend the poster session and ask more questions to the speaker. So with that, let me close the session, and thanks all the speakers and